Okay, in this section, we're going to go back. We're going to actually look at finding the center of mass of a lamina, which is also called the centroid. A lamina is just a thin, flat sheet of material. If we go back and we think about what happened in Cal 2, what we did was we took some bounded region. Let's say I'm bounded on the top by a curve f of x, and I'm bounded underneath by a curve g of x, and I'm going to look at this on the closed and bounded interval between a and b. And in doing this, I'm creating then this lamina, which is this thin sheet of material. So what we did here, and this is going to be our review from Cal 2, is the first assumption we made was that our lamina had uniform density. Now, assuming that this lamina is made up of the same material throughout, then we can think of density as thickness. So we're going to assume that our lamina has the same thickness throughout, and we'll just call that lambda and let it be constant. So lambda in this case is constant. So how did we go about this? Well, what we did was we partitioned this closed and bounded interval from A to B into n equally spaced partitions. I'll call A x naught, then I'll come over here at x sub 1, then x sub 2, then x sub 3, and so on and so forth, all the way till I get out to x sub n. And what we'll do is we'll come in here and we'll create ourselves a bunch of rectangles, assuming that they're all equally spaced, and I'm just going to grab them at certain points here. It doesn't really matter where, because again, how many rectangles are going to wind up with in the end is an infinite number of them. And so then we looked at this, and remember, the center of mass is the balancing point. So in other words, if I could take this lamina and pick it up and then hold it with my finger, where would I have to place my finger in order to balance it? So the first thing we did was to realize that for each of these rectangles, since the density or thickness was constant throughout, the center of mass for each one of these individual rectangles was the intersection of the diagonals. That's just geometrically what the center of mass would be for those rectangles. And then in doing that, we came up with this particular system now, which just contains some individual point masses. And so in a point mass system, we know that the center of mass is the ordered pair x bar, y bar, which by definition is equal to the moment about the y-axis divided by the mass of the system. That's where we get the x bar coordinate from. And the moment about the x-axis divided by the mass of the system. And that would be where we would get the y bar coordinate from. And then we defined each of these quantities. We started out by looking at the mass of the system. Well, by definition, mass would be equal to the density of this system times the area. Well, the density, remember, we said was a constant, which we called lambda. So we've got our density. And we have calculated the area of a bounded region between two curves. As a matter of fact, if you look at the way I've set up these curves, I can clearly pick out a top and a bottom curve, so that the area would be defined as the integral from a to b of f of x minus g of x with respect to x. So using this, we then get the mass of the system. Now, let's take that same concept and convert it over to Cal 4. Okay? Now, in Cal 4, one of the first differences we have is that the lamina no longer has to be uniform. So the lamina can have a varying density. And as a matter of fact, it can actually be some function lambda of x and y. What does that mean? Well, if you think about it, then as you move through different points on your lamina, the thickness can be changing, and we can define that thickness just simply by using x and y coordinates to make that determination, or some function of x and y that'll help us determine the thickness at any given point. Well, in doing this, then again, the center of mass is still going to be the same thing. It's going to be considered to be x bar, y bar. But we've seen, so let's go ahead and do the calculations there. Mass, once again, will be equal to density times the area. Now, we've seen in Cal 4 that we can actually use a double integral to calculate the area, and we're going to do that here. But notice that our density is no longer constant or uniform. That means that it's some function of x and y, meaning it cannot be pulled to the outside of the integral. So we get that the mass will be the double integral over the region of lambda dA. Why is that? Well, remember, to calculate the area, we simply need to look at the double integral over that region. And of course, our density now is changing, so we don't necessarily get to pull it out. Let's look at some other differences between what we learned in Cal 2 and what we learned in Cal 4. Going back over to the Cal 2 side, there were 3 calculations that we had to make in order to determine the center of mass. They were the mass of the system, little mass, and we've defined that for both. We also needed the moment about the y-axis. Now, by definition, this is the distance from the y-axis times the mass of the system. Well, the distance from the y-axis is simply x. That's how we determine how far out we get. We go a certain amount x, and that tells us how far we are located away from the y-axis. So this is just the same thing we saw here for mass times the distance from the y-axis, or in other words, back from Cal 2, this was lambda times the integral from a to b of f of x minus g of x, all times x with respect to x. Again, the reason for that is we just needed to multiply this by the distance we were located away from the y-axis. Well, that same thought process is going to hold true in Cal 4. That is, the moment about the y-axis is going to look like this mass times x. So this is going to be the double integral over our region of lambda times x dA. So far, we haven't done a whole lot other than to change the way we calculate the area in our system. Now, if we go back and we think about Cal 2, though, this was not the problem calculation. The problem calculation was the other one we needed, which was the moment about the x-axis, because the moment about the x-axis is defined to be the distance from the x-axis times the mass. But what is the distance from the x-axis? It's y. And the problem became we could not put a y into a dx. So what we had to do instead, let's come back up here and look, we needed to figure out what this coordinate was here in terms of y. And it's just something in the center. So how did we figure that out? Well, what we did was we took the f of x value right here and the g of x value, and we just looked at what the distance was halfway between them, because that would give me what the y value was here. And the distance between those is simply the average. So instead of just taking the mass and multiplying it times y, the moment about the x-axis became lambda times the integral from a to b of f of x minus g of x, which was your area, times instead of y, we had to use the average of f of x and g of x, which look like f of x plus g of x divided by 2 dx. And again, the reason behind that was because we could not put the y into a dx integration. Well, here comes our Cal 4. And in our Cal 4, now we're integrating with respect to multiple variables. So when we calculate the moment about the x-axis, we are absolutely allowed then to put in a y variable. So this simply becomes a double integral over the region of whatever our density is times y dA. And we get a much easier set of formulas to use to calculate the same things that we did from Cal 2.